Dr. Button he's an alumnus of our department, okay? So we have someone here who's a card-carrying DMSE member, so he knows certainly what we are. And he's been, of course, a longtime friend and supporter. But I can also say that Dan has been in orbit around MIT, not only since he was here, but long after. And so he's a member of the innovation ecosystem that surrounds DMSE. And you could tell already at the time that he got here to take up his PhD that he was going to be someone who would seek vertical integration. So he came from Cornell, and he took a bachelor's degree at Cornell in material science and engineering. And I just want to do some foreshadowing here. So back at that time already, as a 21-year-old, he had majored in material science and engineering with two specialties, physics and economics. All right? So what says more about aspiring to vertical integration than those two specialties? He came here and took his PhD. He worked with Professor Harry Tuller on that. And his thesis title, this is some deep science here, so I'm going to read it to you, Structure-Transport Relationships in Amorphous Oxide Systems, Fast Ion Transport in Alkali Borate Glasses. So he got a PhD on a very highly technical subject. After that, though, he went out into the industry, and he has worked in a variety of really interesting positions, both in large corporations and in a number of startups. His career spans from R&D to business development, technology acquisitions, and a series of senior leadership roles in startup companies and rapid growth technology companies. You may have heard of some of the MIT-affiliated companies that he has been at the top of, and these would include E-Ink, Boston Microsystems, and QD Vision, among his many other roles. So what I love about this story is that we've got the Course 3 alumnus come home, we've got the scientific depth, we've got the business experience, and we've got the startup experience. If you want to understand innovation and how materials connect to the innovation ecosystem, Dan Button is the guy to tell you about it. So, without further ado, let me introduce today's speaker. Please join me in welcoming Dr. Daniel Button.
Are we on? Can folks hear me? Great. So good afternoon, and welcome to the wild and wonderful world of material science startups. One of the really seductive things about material science is its interdisciplinary nature, and it truly is transformational in unlocking new frontiers, and it does that by introducing new properties, new functional capabilities, and new applications. And I'll be showing you some of those examples. I've been very fortunate to have been a part of many of those, and haven't invented any of these things, haven't founded any of these companies, but fortunately I was able to be along for the ride. By its very nature, material science is truly on the cutting edge, and I've been fortunate to have spent my career on the cutting edge ever since I got my PhD here. Harry and I were a little bit ahead of our time. We were developing solid electrolytes for high-performance lithium batteries. We were off by 1 or 2 decades, but they have come to roost. But I really would love to take advantage of this to thank the department for launching me on this fantastic journey. And it really, as Chris said, I've been kicking around here for a while, and it's really quite comforting to look around the room and see plenty of folks that were with me way back when at the start. There's Harry Tuller, who was my thesis advisor. Don Sadaway, the first time he taught kinetics, the 321, I was one of those fortunate students and actually understood kinetics after taking the course. Yet Ming was a colleague of mine in the graduate program in ceramics way back when, and it's such an honor to give this lecture in honor of Dr. Wulff, and looking forward to sharing a part of my journey with you. So let's see if we're going in the right direction. Oh, just a sec. So I recognize this cliff. So there's no question that if you're in material science startups, you are on the leading edge, you're on the cutting edge, and it's an incredibly exhilarating place to be. And for many of us, it's the only place to be. But it does have its moments of suspense and drama, and its challenges in terms of commercializing the technology. And so what I want to do today is just share some of the lessons from many different experiences bringing products to market in large companies and small ones, because there are a handful of what I would refer to as key success factors, particularly for material science startups. See, the cutting edge is absolutely essential. If you're in a startup and if you don't have a disruptive technology, if you are not on the cutting edge, you simply don't have a prayer. Because just think about it, your competition, they've been around, they have experience, they're often big companies, they have money, they have people, they have factories, they have loads of patents and partnerships and reputation and brand. And you're going up against this with a new technology with a minimal amount of any of those resources. So the cutting edge is really a rite of admission. As many of you have heard, it's necessary, but it's far from sufficient. So the cutting edge is an area that sprouts startups, and any sprout needs nourishment, needs sunlight and water, and in the case of a startup, that means you need financing. And to finance a company, investors have a lot of different factors, and so you're expecting people to turn over millions of dollars to you. And so they're pretty careful about checking you out, and especially in the material science world, I've found that two of the most important factors are time to market and capital efficiency. And it turns out that these are what are probably the two most fundamental resources. Of course, the ultimate one is intellectual capital, but they're highly intertwined. And first amongst these is time to market. Time to market is, you might imagine, all sorts of wonderful things happen when you get your technology to market. You validate it, it's the ultimate validation. You're making money, and you're on your way to profitability and financial independence and an exit for your investors. But not only is it an important point to reach, and you want to spend as little money as possible getting there, but the fact of the matter is there's this very important concept to be aware of in the startup arena, the high-tech cutting-edge arena, and that is the concept of shit happens. And unfortunately, it happens all the time, and the more time you have, the more likely shit is to happen. And this is a very technical term. I'm going to try to limit the number of technical terms I introduce today, but this is an important one. And what does that mean? Well, it means that over time, ultimately, if you take too long to get to market, someone is likely to invent and introduce something that's better than you. Or all the customers adopt something and commit to it, and by the time you come along, it's too late. Or your investors get tired of you, or they change their priorities, or your partners or your customers. So, and I've experienced every one of those things, probably more than one time. So you really want to have an enormous sense of urgency to get to market quickly. I will say that getting to market quickly, in my experience, is without question the biggest competitive weapon for a startup or for any business, but I will save that topic for some other lecture. Capital efficiency. So just think of it. The more time that you take to get to market, the more you have every month you have to pay your staff, and you're spending more money. That means you have to raise more money. And that introduces all sorts of problems. It introduces financial risk. The economy may go into a recession in that period of time. And Lord knows that's happened in the venture capital community several times in the past 20 years. Capital efficiency, the more money that an investor has to put in, the lower their return on investment. The more money that goes into the company as a founder or an employee, you're going to get diluted, so your share of ownership goes down. And also, if you're an employee or a founder, the higher the hurdle is, because the way investments are structured, the investors get all their money first before anyone else gets a dime. So you want to have that capital threshold as low as possible, not as high as possible. So there's no question that time to market and capital efficiency are paramount. So, of course, it begs the question, how do you do that? But before I get to that, let me start with really where the particular fun is, and that's the cutting edge part of the equation. And that's what's so cool about material science, because it is the cutting edge. This is a cool chart that's compiled by Professor Yetmin Chang. He showed it at a visiting committee meeting last fall for the material science department. And it just shows all of the companies that have sprung out of the material science department in the past 20 years. And there have been quite a few. In fact, 45, the problem may have been one or two since this was compiled, but since 1987, there have been 45. They've been founded by a combination of professors and students. Many of them have had exits, either initial public offerings, M&As, or merger and acquisition. That's the company got bought, and a ton of licenses of DMSC patents. Actually, Yet's a poster child of the startup arena. He was one of the founders of American Superconductor, co-founders back in '87. He was a co-founder of A123 Systems, arguably the highest exit of a material science company in this area in the past 15 years. $1.5 billion yet? Ish. And then more recently, Yet's co-founded 24M, a battery company, and Desktop Metal, a 3D printing company of metal objects. So if you're interested in starting companies, you have found the right place. I've been fortunate to, as I mentioned to you before, to have worked at a number of companies with cutting-edge technology, in many cases technology that has changed our world. And in fact, the first example is DuPont. Our business team in Japan developed a screen-printable circuit material, and it was a breakthrough metal ceramic composite, and actually it was invented by an MIT material science grad, Mark LeBranche. Probably some of you may remember Mark. Well, we did this in collaboration with Toyota, and in 1990, we enabled the world's first under-the-hood electronics. So believe it or not, before 1990, there were no under-the-hood electronics, and of course, today they're ubiquitous. But that didn't happen by accident, and there were a lot of pivotal things that were done to achieve that. I was fortunate to be at Corning, their LCD glass business. Today, just about at least 1 out of every 2 LCD displays, any display, is made with Corning glass. They dominate that industry. I was there when it was a young business, up until about $150 million in sales. This was built, actually based on an innovation, a process, a fusion glass sheet forming. That actually is a trough up there. And it's very clever because if glass that's been fused and never touched anything is pristine, has no defects on it. And so the holy grail is to have a glass object that has never touched anything. And the way they did this with the fusion process is they have this trough, they fill it up with molten glass, it spills over the edges, runs down the sides. As you can see, the sides are tapered, and then the glass comes together at the bottom, and so the outside surface was always molten. It's a very clever approach, and it makes the world's most pristine glass, semiconductor-grade glass, which you need for the LCD industry. They enabled the LCD industry with this technology. What's interesting is it was originally developed to make windshields 30 years before this, and Corning dusted it off the shelf to make LCDs. And on the basis of this very clever process, using the in-house capability, we worked with Sharp, and now, of course, this business underpins Corning. It's a multi-billion-dollar company. Actually, it's not 50% gross margin. The gross margins for this materials business is 70%, which is enormous. E-ink is a great e-ink MIT story. This technology came out of the Media Lab. I think many of you may not know e-ink, but you all know the Kindle and e-reader devices. E-ink is the industry standard for paper-like displays. And it's a very clever technology. It starts with these microcapsules, and these are literally on the order of microns, and they're filled with a solvent, and you oppositely charge carbon black and titania. So these are the same black and white materials used for newspaper print, and they're highly reflective, just like ink on paper, and they're oppositely charged. And so what you do is you have these capsules, you coat them on a film, and then you have an electrical array to address them. And so just think of it this way. Let's say, I can't tell which positive and negative from here. It's a bit blurry. But let's say the white particles are positive. What you do is you just apply a negative bias to the top, and all the white go to the top, and the negatively charged goes in the opposite direction. And if by tailoring the amount of you can actually get a large number of grayscale in between. And on the basis of this simple technology, the company was able to establish this as the industry standard for paper-like displays, and we went to market with Sony with their first e-reader device, and then ultimately a Taiwanese company called PrimeView bought e-ink, and then they've adopted e-ink as the name because the brand was so strong. Boston Microsystems, certainly near and dear to my heart. Harry Tuller and Rick Mulchuk, his graduate student here near the front row, founded this company in 1997. It was actually based on a breakthrough in micromachining. And up until their invention, you only would micromachine silicon in one direction. So one material, one direction. Harry took a diamond-like material, Harry and Rick, and they discovered that if you shine light with the appropriate energy level relative to the bandwidth, that they could take standard materials that would dissolve silicon, and they would take this diamond-like material and transform it into almost like sugar and water in terms of micromachining. And so suddenly they could make remarkable devices with a diamond-like material. They used this as a basis for RF resonator devices, which underpinned trace chemical detectors. Actually, the world's most sensitive trace chemical detectors. This company was ultimately bought by Paul Corporation, who uses it for ultra-high purity filtration of gases and liquids. QD Vision, classic nanomaterial. Vlad Bolovic, Monji Buendi here at MIT, and their team invented this. Basically, what's cool about this is it's like a phosphor on steroids, and you can activate, it emits light, and you can activate the light with either electrons or photons, and by controlling the size of the nanocrystal, you directly control the wavelength of light that's emitted, and so you can get the world's purest colors. And so it was a logical place for the display industry. Actually, Samsung just bought QD Vision last fall, and you may be familiar with QLED TVs that are based on quantum dots. But that's a picture of a 5 nanometer quantum dot. You get down to 5 nanometers, and you're talking about tens of hundreds of atoms. You're not, and wonderful things happen from a quantum scale. Innova Dynamics, this is a UPenn spinoff, actually founded by 2 undergraduates in their thesis project. And what they did is, it's a way to create nanocomposites where they take silver nanowires, they form a special ink, they coat a plastic film with this ink, and the ink is designed to dissolve the surface. The surface softens, the silver nanowires sink into it, the ink's designed to evaporate, the molecules recombine in the polymer, and you end up with an amazing composite structure. And because of the drying process, it actually forces the silver nanowires together for good conductivity. And a natural application for this was touchscreens. And last year we executed a M&A transaction with TPK, the world's largest touchscreens company that now holds this technology. And then most recently, I've gotten involved finally with a spin out of my alma mater, Cornell. It's a 3D computer vision technology. And it's pretty cool. It takes advantage of the wave properties of light, which has phase and directionality, and it's the only 3D sensor that directly measures depth or direction as well as 2D image, and it's a single sensor solution. All other solutions, like on an iPhone 7, the coming iPhone 8 has 2 cameras or many other components. But this story has yet to be told. We just finished our seed financing. So, lots of cool things on the cutting edge. These all started with really neat, promising inventions. And oftentimes people will cynically say, well, okay, the invention's made, it'll sell itself, or now it's who you know. And it does help to have a good network, but it's not who you know, it's what you do. And so that's where I'd like to spend a little bit of time going through each of these and just talking examples and talking about 1 or 2 key success factors. And they're really grouped into 5 areas that I've found, and myself, and obviously I'm not alone in this, the people that have taught me, the people that have worked with me, that make a difference in getting to market quickly with as little cash as possible. And by the way, before I dive into these practical strategies, obviously there are other important things that matter. You need to, you need the right business model. You need to pick the right market. You need to pick the right partners. These are obviously all extremely important. But if you want to get to market quickly and use as little capital as possible, you want to pay attention to these 5 things. So focus. One of the biggest mistakes startups make, and this is particularly true of material science startups, is they don't focus. The problem is that these inventions can be applied so many different places. Where do you begin? The 3D camera company that I'm now working with, running, is we could get into smartphone cameras, we can get into virtual reality headsets, we can get into auto collision avoidance systems, we can get into drones, we can get into robots. I know that at least the short right answer is you don't do all of them at once. In our particular case, we're going to go into smartphones, but you just have so limited capital. You want to do it quickly. You have to be incredibly focused everywhere you possibly can, and that means you pick one platform to develop. You pick one market. Within that market, you pick one application. Within, you don't work with 10 customers. You pick 1 or 2 key customers, et cetera. It's just hugely important to focus. And I'll give an example, one being e-ink, where we didn't start out focusing enough, and it cost us $50 million. It was an expensive mistake. Drop-in. Basically what drop-in means, you want your technology to drop into the world and leverage everything possible that exists within the world. You don't want to reinvent anything. You've had your invention, you've created something that's special. You're not going to be God's gift to manufacturing or all these other areas. So focus on what you do well and then leverage the daylights out of everything else, because you don't have the money and the time to build factories or to invent complementary technologies or brand new material for your supply chain. So you want to drop into the ecosystem. Ideally, you want a technology or product that just drops in so seamlessly nobody has to change anything to adopt it, because if they do, if they have to invest money and time and engineering, it's a huge barrier. Design-in. I didn't learn about design-in until I was running that electronic materials business in Japan, and we worked with Toyota. Design-in is it's really proactively developing your technology around an end customer's product when they are beginning to design their product early in their process. In fact, I'll give you an example at Corning where early in the company's history, I just joined Corning, we weren't using design-in, and it almost destroyed that business. But design is a critical success factor, especially for material science companies, because materials tend to be lower in the value chain. Now, you'd like to go up as far as you can, but if you have a material startup, you're not going to become a phone company, and you may well not become a display company per se. So you need to learn to work with those people at the top of the chain. Practice, and I really mean practice. But by practice, that means take your technology that was in a laboratory and practice it in production. Practice it at making large numbers with equipment that scales. Practice it in the end product. So at e-ink, for example, yeah, we made these microcapsules, but we were building full displays with full functionality to learn how it worked, to optimize the software, to help our customers optimize the software, to test reliability. Practice is really important. You'll see Corning is, we're really world-class when it comes to practice. And then there's diversify. And at first glance, this may seem at odds with focus, but it's a different side of that coin. When I say diversify, it means diversify to manage risk. And so diversify means, so what are your key risks? Well, if one of them is developing a key part of your technology, have a contingency approach. Don't have just one approach. Or for financing, have more than one source of financing because, as I said earlier, shit happens and you lose investors and you better have a backup. Actually, one of the testimonies to Boston Microsystem's success was the diversity in financing, as I'll mention in a moment. Diversity of the team. You want a team that's versatile, that if they have to change directions, they can do that. So there's five different things, and if you're like me, it's probably may not mean a lot to just hear me talk at you about these different approaches. So what I'd like to do is try to bring them to life with each of the companies that I was a part of. So I'll show you, starting with DuPont. So, you heard me say earlier, materials science, we enable everything, but we tend to be lower in the chain, and that was very much the case at DuPont. So DuPont screen printing, what we sold is the inks that are screen printed and fired to form circuit materials. And the key thing that prevented any underhood applications of electronics was the severe environment in an engine area, not just the horrid chemical environment, but the thermal shock. Because the fact is, markets like Montreal and Minneapolis, it gets down to minus 40 all the time. And you have tests where you have to go 105 to, in fact, this is a key issue actually for other technologies like batteries, but you have to swing from 105 to minus 40 or 140 to plus 140 to minus 40. That is pure hell, as you might imagine, on materials. So the breakthrough here is Marc Lebranche developed a metal ceramic that could withstand the thermal shock of a car. And it was some very clever adhesion promoting material science that he developed. But DuPont sells inks. We sell inks to a company that Noritake, that prints the ink to form a circuit, that sells it to Nippon Danso to make an electronic system, in this case an anti-brake skidding system, and they sell to Toyota. And the way, really the only way that you have a breakthrough in material science for an automotive industry is you have to collaborate. And this is designing. So we actually collaborated directly with Toyota at the top of the chain. We actually involved these partners. And I proudly say that my main contribution to this is I came into a business leadership role. This project was already happening underneath me. And to my credit, I did not screw it up. And that's an important area of contribution sometimes. So Corning. A perfect place, actually, for someone who just learned about design in to end up. The display industry is just absolutely unforgiving. Just look at the size of a display glass over the decades. When I arrived at Corning, the standard size, it was Gen 1, it was maybe 12 inches by 12 inches. Today, they make glass that's 3 meters by 3 meters. And they do it with incredible precision in terms of dimensionality and absence of defects. In fact, up here is a picture of today's current generation. You have two people standing by this, and there's 6 TV panels that come out of that sheet of glass. Imagine handling this, packaging this, making it. It's really an amazing feat. Well, the display industry is a lot like the semiconductor industry. You've all heard of Moore's Law. And what drives the semiconductor industry are generations of technology, and usually it's the size of the wafer and the fineness of the feature sizes that you can create. And it's similar in the display industry. And to a large degree, especially in these early years, every 2 years you had to come out with a new generation and increase the size by 4 or more times. And the fact is that everything I just said about difficulty of that glass, your customer has that same challenge. So they start at least 2 years earlier to introduce a new generation of glass. Well, at the very beginning, I'll tell you that Corning is a best practice at practice, and today they're a best practice at designing, but they were not here. And when they introduced its second generation of glass in the '93 time period, the first time that Corning sampled that glass to their key customer, Sharp, was after Sharp built the factory and designed all the equipment, and the worst thing in the world happened. They tried to use that glass, and nothing stuck to the glass at all. And this is a good example of why it's good to be proactive. And it's good to start with your customer. And what's interesting, what happened is that alkali components will poison the transistors. And so Sharp used to put, in Gen 1, they would put a barrier layer of pure silica between the glass substrate and the metal structure, and the silica was a wonderful barrier to the alkali. Then Corning was a victim of its success, got rid of the alkali. They eliminated the barrier layer, but they never tried, no one, until they were ready to turn the factory on, ever tested metallizing the bare glass, and it didn't stick. The good news is Corning reacted quickly. We worked closely with Sharp. We invented a process. We scaled it up in Japan, got it qualified. And within a year, even though we lost half our business because the industry doubles every year, we were able to recover. And of course, as you might imagine, Corning is world-class at designing today. But it's really, for me, an incredible lesson in just how important designing is, especially material science. But I will say, working at Corning was a blessing for me. It's world-class at bringing new technologies to market. As you know, they have helped transform industry after industry, whether it's light bulbs or railroad glass or TV glass or optical fibers or now LCD glass. And they are amazing. And they have a very structured process that forces you to practice, both in terms of manufacturing and making an end product. They call it making some that work. So it's that discipline that allowed Corning to recover so quickly, despite our design and shortfall. So E Ink had its hard learnings. So as I explained earlier, the core of it is this simple microcapsule. And you coat it on a film, and then you build up a circuit where you have an addressing circuit and then a top plane, and you apply voltage in a specific way to image it. The big mistake E Ink made is they overreached. They did not focus. Here they have this wonderful technology, but they decided that they would make displays themselves, so they literally started making 3-foot size displays, which means you have to build a factory to make 3-foot size displays. These displays were addressed wirelessly, so Motorola invested in the company. You entered in the text over the internet, so you needed that infrastructure. They were way over their head. They built all this infrastructure. They weren't world class at it. They spent literally $50 million building this business and then pulled the plug on it. Now the good news for Inc. is they live to fight another day, and we brought the next product that we did bring to market, and I was fortunate to be a part of this, is we focused on where we were strong, and we made, instead of going way up the chain, we made it the key component that, so you take that and you code it. Now coders cost tens of millions of dollars and require lots of experience, so we partnered with somebody, Topon Printing, to do the coding, and we designed in several rungs up the chain with Sony, to get it to market. And so after we stumbled, we used design in to drop in, and we got the first product to market with Sony in actually record time. Once we focused, we got it to market within 3 years, and it's now an industry standard. That company is $600 million, quite profitable, and actually they continue to have a major presence here in Boston Microsystems. So really cool technology, micro-machining diamond-like materials to make resonators. This happens to be a silicon carbide base, and then aluminum nitride is epitaxially grown. So these are all single crystals, and it turns out silicon carbide provides a wonderful template for aluminum nitride epitaxial growth. The aluminum nitride is a piezoelectric material. You apply an AC current to it, and you put it into resonance, and then you put a chemical selective material on that, absorbs whatever species you want, changes the weight, and it's designed so that a measurable amount of frequency shift can correspond to an incredibly small weight change, and that's because that paddle is so small itself. The problem is it didn't end there. To successfully bring this to market, we had to embed this in a microarray. So there are 2, 4, 6, 8, 16 of these. So that's okay, you're scaling up, good enough. The problem is now we had to invent a pre-concentrator to collect the species that we would then release onto this to get it to work. But on top of that, we needed special low noise electronics to read the signal. And so suddenly the focus of resources of time and money is strained. Now the good news is we had other things going in our favor, and that is diversification in 3 important areas. One is the technology can serve all sorts of different markets. So even though we started in Homeland Security, which is in the end a nasty market to enter, particularly any government market is hard, went into, actually worked with Corning on NOx emission detection, and then ultimately hit the jackpot with measuring water at the lowest levels that anyone can measure today. You don't want water in any kind of semiconductor manufacturing process, and that's why Paul bought us. But the other part of diversification is the team was incredibly versatile and resourceful and was agile enough to develop all those technologies and to move between those different industries. And then the third key success factor from a diversification point of view was financing. Remarkable ability to not just raise equity, but government money. And that really gave BMS the time to pivot and ultimately prevail. So diversification matters. QD Vision. I've got a number of colleagues here from QD Vision. Hey, guys. So, QD Vision and Nova Dynamics, two of the things I'm particularly proud of the teams of is that we got to market first, despite competitors that had literally multiple times more capital and had been in the market 5 to 7 years longer than we had been in the market. And a key success factor was focus. And when I say fraction of the money, we're talking like 24 million compared to 150 million. And in terms of time, in this particular case, our arch rival was founded around 2000, and we beat them to market in 2010 with a solid state application. And in fact, we got to market quickly with a solid state application for LED lighting, and it was exactly the same technology for TVs. We started with solid state because you only needed red, but for TVs you needed green, so we needed an extra year or two to develop green. But we did successfully. Frankly, QD Vision is an example of all the different strategies. We focused heavily, dropped completely into the supply chain, designed in with an industry leader, ultimately Sony. A lot of practice, and a very talented, versatile team. Nova Dynamics, actually, a very similar story. Through focus, we got to market 5 years. We got to market at the same time our competitor did, even though they had a 5-year head start. And we did it about 20 million versus 120 million in capital. And frankly, the biggest success factor was focus. From the very beginning, we focused on transparent conductive electrodes because we could embed any particle in any polymer. But we said we're going to embed silver nanowires in plastic films. But transparent conductive electrodes are used in solar, displays, touch sensors. There's all sorts of markets. We focused on touch sensors. We had a strong value proposition. And then, as you know, touch sensors are used everywhere. But we specifically focused on mobile devices. And with that hyper-focus and leveraging the daylights out of world-class players across the value chain, we got to market quickly and cheaply. So BSF, who was an investor, made the silver nanowires. PPG made the inks that were sold to DNP that made the transparent conductive films that were used by TPK to make transparent conductive sensors and screens. We also, practice was very important, so we would we would rent production scale equipment to do the coding long before we started working with DNP. So by the time we showed up at DNP, we knew it was going to work. By the way, well, I mentioned TPK ended up buying the technology. So, there are, hopefully this brings to life for you a sense of, why practical strategies matter. Hopefully you can, understand that time and cash matter. These aren't the only things that are important to succeeding, but I would suggest that if you're not doing one or two or at least one or two of these things in a material science startup, you're probably in trouble. And if you do all 5 of them, wonderful things can happen. So the bottom line is you start at the cutting edge. So if you care about being in a startup, you're in the right place today because material science is a wonderful haven for being on the cutting edge by its nature. But then you do what it takes to get to market quickly and to spend only the money you need and no more than that. So with that, I'd like to thank you for your attention. If we have time, I'm happy to answer questions. Thank you. By the way, one other, while I would be remiss if I did not thank people, especially there are many people in the audience. I've been a fortunate student, and my teachers are everywhere in this room. My colleagues from several of my companies, particularly BMS and QD Vision, mentors that I've had, like Joe Maressa. Of course, Harry was one of my earliest mentors. Colleagues within the department. I've been very fortunate, and just like to, for those of you that are here, really heartfelt thanks for having me join your journey. So, thanks.
Fantastic. Well, I don't know about you, but I feel like I'm taking up too much space, not on the edge. So thank you for that inspiring talk, Dan. I think we do have a few minutes that we can entertain questions, and I will give preference to youth in the questioning here. So please go ahead and raise your hands, and then I guess I'm going to have to be the judge of youth. Actually, I'm sorry. No, yeah. Please, go ahead.
Yeah, thank you for the great talk. And so you mentioned focus as obviously something like very important. And a lot of the examples that you give, like you had that focus and it's almost like you nailed it. But there's also the notion in startups of, pivoting.
Correct.
Like you have to pivot. So is that something that's relevant to material science startup? And so how do you deal with that? Like how do you?
Yeah. Well, first of all, remember I talked about, these are important practical strategies, but your business strategy is paramount. So you need to pick the right business model, the right product, the right, like I said, the right market, application, et cetera. So defining strategy is a hugely important question, but often you don't get it right. And that's where diversification really matters. And BMS is just a great example of persevering because of that. They could pivot to other markets. They had financing that was diverse and the capability that was diverse.
Thank you. So please go ahead. Oh. All right. Are there any other questions from the floor? Please.
Yeah, Dan, strong leaders become strong leaders because they fall off the cliff. Get back up. Climbing up the mountain. So could you talk a little bit about how your leadership evolved, some of your leadership lessons? Because you can't succeed in any endeavor without strong leadership.
Yeah. This is my leadership coach. He's nailing me with a tough question. But actually, no, it's a very important question. Part of it is having good role models, or being blessed by having good role models earlier in your career, and also part of it is recognizing important skills and working on them. So in my particular case, I was fortunate to start my career at DuPont, and DuPont really values working through people. And in fact, 6 years out of grad school, I had 30 PhDs reporting directly to me and another 30 technicians. And you can't micromanage these people. I mean, you really have to learn how to empower. So I was kind of thrown into the deep end there. I've been fortunate to have had some amazing role models, also people that are patient. And also, in my particular case, and this is a challenge, I think, for young technical types, is emotional intelligence isn't always our strength. And if it is, God bless you, because if you have the combination of intellectual horsepower and emotional intelligence, you'll take over the world. But it's certainly an area I've really focused on to develop, and it's made a huge difference. Learn how to ask questions as opposed to provide answers. In fact, at the end of the day, a hallmark, I think, of good leadership is asking the right questions, not providing the answers.
We'll have time for one or two more. Please, go ahead. Yeah.
You are emphasizing startup businesses, but aren't there mature businesses that need high-tech technology? Because I can illustrate that. I first dealt with Corning glass, and I'm probably the oldest one here, and I wanted them to help me on a process. And I considered them very backward at the time. They were lazy, and they had, I was unable to even...
What business was that, by the way?
Something happened between 1950, 51 period, and the period you're talking about. They must have reorganized their technology or emphasized it because they changed.
Yeah.
So I think that I don't believe everybody here is going to have a startup opportunity. So I like to speak to the more mature industries, in fact, can provide an exciting career for people because you can bring in a concentration of very high-tech, integrating different, the physics of the process, heat, material properties, and so that I think that there are opportunities in a mature industry. You have to look for them. So I didn't want to have everybody.
Oh, sure, sure.
Think that everybody's going to be in a startup position because you can, even in a mature industry, you can have a startup situation.
And I was fortunate to be part of some of those. But, very good point. The first half of my career, I was in Fortune 500 companies. The sad thing is that fewer and fewer of them are doing, R&D. They're abdicating it to a large degree to the startup community. Corning is thankfully a great exception. They still have world-class R&D, but I will say this though. A big negative for startups historically has been, it's uncertain, you have to rely on financing and all that good stuff. And the sad reality is in our economy today, in this gig economy, there is no 20, 30, 40-year career anywhere. But some people will be very happy in large companies. You can accomplish a lot with their resources. And you unfortunately, you may not have the security you used to have, though.
All right. So thank you for that. That's fantastic. So in light of the time, I think we'll go ahead and stop it here. However, on behalf of DMSE, the Department of Material Science and Engineering, lest you forgot, we would like to invite you to join us just outside these doors where a whole lot of food has been laid out for your perusal and enjoyment. And if you can join us, Dr. Button will be there to take questions personally. So thank you for joining us this afternoon. Please, another round of applause.